Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 17th part of the video series. So we have come a long way. In this video, I'll be explaining one of the most interesting concepts of this chapter, that is Lensmakers formula and Lens's formula. We'll be deriving both the formulas and look into some of the numericals based on this formula in order to solidify the concept. Then we will dissect this formula and look into the parameters on which Lensmakers formula depend. There's one parameter in this Lensmakers formula. If you change that parameter drastically, then what happens is convex mirror starts behaving as a concave mirror, or we can say that concave mirror starts behaving as a convex mirror. And we'll also look into that parameter. So it's a special kind of situation. We'll be looking into that. We'll also solve one of the numerical based on that situation so that that concept becomes solid to you. Okay, so there's a lot of concept that I need to explain in this video, and also we'll go through a number of numericals based on those concepts. So without any further delay, let's jump into the video and start building our concept. So let's start our study on the concept of Lensmakers formula. We'll be deriving the formula here. Now if you haven't gone through my previous video, then it will be difficult for you because we'll be using that formula here to derive this concept. Okay, so let's see. We know the formula for refraction due to curved surfaces, the image location is given by mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r, where r is the radius of curvature of the curved surface, and mu2 and mu1 are the refractive index of the medium, where mu2 is the refractive index of the medium in which the rays are entering, and mu1 is the refractive index of the medium from where the rays are coming. Okay, so let's see, we require two rays for image formation. So this is our first ray and this is our second ray. Okay, this second number ray is moving along the principal axis, so it will not deviate, it will move along the principal axis as you can see. And the first ray after refraction bends towards the normal. Why? Because as you can see, mu m is air and this is mu l, that is refractive index of glass. Maybe it is made up of glass, and we know that refractive index of the lens is greater than the refractive index of the medium, since the medium is air. Therefore, as the light is entering from optically rarer medium to denser medium, therefore after refraction the ray will actually bend towards the normal. Therefore, as you can see, this will be the ray diagram. Now I haven't taken into consideration the second surface. This is the second surface. Okay, so basically what you can see here, lens is actually combination of two curved surfaces, this one and this one. So we'll take one at a time and see. Okay, so in the first case, what we have done, we have just considered the first surface, forgetting about the second surface. Okay, so after refraction from the first surface, what happens? It bends towards the normal and meet here. So the image that is formed due to just refraction from the first surface is this one. So this is the I dash. Okay, that is the image produced due to the first surface. Okay, now let's understand. If this is the object distance from the optical center is u, isn't it? The lens is a thin lens, that is what we have considered, and the image distance that is produced due to refraction from the first surface is taken as v dash. Why v dash? Because this is not the final image. Okay, there will be again refraction in the second surface. We'll be looking into that. So if you use all the data that we know, and this is the radius of curvature of the first surface, we'll be taking into account this one also. So if you use all this data in this equation, then what will happen? Mu2 here will be mu l. I hope this is clear. I've explained this in my earlier video. And v, that is the image distance here, is v dash minus mu1 is that of the medium, and u, that is the object distance here, is u. Mu2 is again mu l, mu1 is mu m, and r is the radius of curvature of the first surface, r1. So this is the first equation that we will get because of refraction on the first surface. Okay, now for refraction in the second surface, what will happen? Let me pick another color. Now for the second surface, what is important here is that the image that is produced due to the first surface will actually act as the virtual object. This concept I have explained earlier, that virtual object for second surface. Okay, we have learned this concept while I was explaining the concept of combination of mirror as well as combination of slab, all those things. I've explained this, that the result of the first combination is actually the object or the virtual object for the second case. Okay, once this is clear, then let's draw the ray diagram and things will be very clear. So the ray after refraction from the first surface comes and hit here, that is the second surface. Now the normal to the second surface is this one, as you can see. Okay, now the rays are actually moving from optically denser medium to rarer medium, isn't it? Therefore, after refraction, it will move away from the normal. Okay, so this will be our ray diagram and the intersection point will be this one. Therefore, the final image will be this image I. Okay, therefore the image distance is this one and we can name this as V. Now let's use this formula for the second surface. What we will get? We will get that mu2, this time mu2 is actually mu m divided by image distance. Image distance, the final image distance, that is V, minus mu1 will be that of the lens divided by object distance. Object distance here is the virtual object distance, this one, that is V dash, as you can see, is equal to mu2 is mu m minus mu1 is mu l divided by radius of curvature for the second surface. So this is our second equation. I hope this much is clear. Now once this much is clear, then everything is easy from now. Okay, so let's look into our mathematics now. The physics is done. Now it's all about mathematics. Adding equation 1 and 2. What will happen if we add equation 1 and 2? I'm doing it a bit faster. You can pause the video and go through that. We can see that mu L V dash and here also mu L V dash, but both have opposite sign, therefore this will get cancelled out. So we can write that mu M by V minus mu M by U is equal to, if you take mu L minus mu M as common, okay, then we will get 1 by R1 minus 1 by R2. Okay, now what we will do is we will take mu m as common from this side, so we will get 1 by V minus 1 by U is equal to, if you take mu m common from this side, then we will get mu L by mu m minus 1 by radius of curvature for the first surface minus 1 by radius of curvature for the second surface. Okay, so mu m and mu m will get cancelled out and we will finally get a result that is 1 by V minus 1 by U is equal to mu L by mu m minus 1 multiplied by 1 by R1 minus 1 by R2. Okay, now we are not done yet. Now let me explain one thing. This is our equation number 3. Okay, so let me write it down. This is our equation number 3. Very simple. It may seem a little bit lengthy, but the concept is very easy. If this is our convex lens, okay, and assume that the object is at infinity, then the rays coming from it will be parallel. We have learned this thing, so parallel rays will come. Then what will happen? After refraction, it will converge to a fixed point known as focus. So here will be the image. So the image distance from the center of the pole will be this V, which is nothing but, since this is focus, it will be focal length. I hope this much is clear. Now if we apply this concept in this formula, then what we will actually get? We will get that since the object, we have considered the object is at infinity, so U will be infinite. So you can write U is equal to infinity and V will be focal length, isn't it? Because the image is produced at focus. So if we use these value in this formula, we will get 1 by f minus 1 by infinity is equal to mu L by mu m minus 1 multiplied by 1 by R1 minus 1 by R2. Okay, I hope this much is clear. Now 1 by infinity is 0, so we will get 1 by f is equal to refractive index of lens divided by refractive index of the medium in which the lens is kept minus 1 multiplied by 1 by R1 minus 1 by R2. So this is our equation, final equation, and we can name this as equation number 4, and this equation is actually known as Lensmakers formula. Because using this formula, people who are expert in making lens, they use this formula to create lens of different focal length. Okay, so since this formula is used by people that makes lens, so this formula is known as Lensmakers formula. I hope this much is clear. Now a little bit is still left. If we look into equation number 3 and equation number 4, that is this equation and this equation, and we compare it, so let me write it down for you, that comparing equation 3 and 4, we can say that 1 by f is equal to 1 by v minus 1 by u. Okay, so this is another important formula or relation which is known as Lenz's formula. Okay, so 1 by f can be written as 1 by v minus 1 by u. Again, 1 by f can be written in terms of refractive index as mu L by mu m minus 1 multiplied by 1 by r1 minus 1 by r2. So these are the two important formulas that you need to remember. Okay, I hope this concept is clear. Now let's dissect this formula and see when can we apply this formula. There are certain conditions, we'll be looking into that. So let's move into that. Okay, now let's dissect this formula, that is Lensmakers formula that we have recently derived, that is 1 by f is equal to refractive index of the lens divided by refractive index of the medium in which the lens is kept minus 1 multiplied by 1 by r1 minus 1 by r2. Now the first point that you need to remember for this formula is that this formula is valid only for thin lenses. Okay. Second, the value of r1, r2 and f, that is this one, and this, if the values are given in your question and you need to use this formula, then you need to use these values with proper sign. Okay, and the sign convention has already been taught. That is, as you can see it here, the direction of incident ray is taken to be positive. So any direction that is opposite to incident ray will be taken as negative. Okay, for example, you need to remember that focal length for convex will be taken as positive and focal length of concave will be taken as negative. This thing has already been explained. So you need to remember this for quickly solving this problem. Okay. Now R1, which one to be taken as R1 and which surface is taken to be R2? Now radius of curvature of the surface on which light hits first should be taken as R1 and the radius of curvature of the surface on which light hits second should be taken as R2. So these are the concepts or the points that you need to remember while using this formula. Okay, I hope this is clear. Now I'll be looking into some of the numerical problems in order to solidify the concept of Lensmakers formula. Okay, so let's jump into that. Okay, let's look into our first problem. This is an easy one. Okay, so let's see how to solve this. Now, as you can look into the figure, that it is a Plano convex lens, isn't it? One of the side is convex, another side is plane. So these kind of lenses are known as Plano convex lens. And ultimately, you can see since the edges are thin and the center is thick, this will basically act as a convex lens. Okay, now if you know that convex lens has a focal length that is positive, see, even without solving, I can look into the figure and can figure out many things. Okay, this is the beauty of concept. Okay, if you have a good concept, you can figure out things just by looking into the figure. So as you can see that it's given that radius of the first surface is 20 centimeter and the refractive index of the lens is given to be 1.5. So what will be the focal length? This is the question, and the lens is kept in air. Now it's very simple, just use the formula and you'll get the answer. So the formula is 1 by f. This is Lensmakers formula. 1 by f is equal to refractive index of the lens divided by refractive index of the medium in which the lens is kept minus 1 multiplied by 1 by r1 minus 1 by r2. This was the Lensmakers formula. Now refractive index of the lens is given to be 1.5, and since it is kept in air, the refractive index of the medium will be 1 minus 1 multiplied by the radius of curvature of the first surface is given to be 20 centimeter. Now you need to check the sign. Now the incident ray will be from this direction. Okay, so this direction will be taken as positive, and we can see that the curve is in this way. Therefore the center will be somewhere here. Therefore this length will be the radius of curvature of this curved surface. As you can see, we measure things from the pole. Therefore, in order to measure this radius, we need to move in this direction, which is actually positive. Therefore, R1 is positive. And we know that for convex lens, the radius of curvature is always positive. So 1 by, we can put the value here, 20 minus and R2. Now this is our second surface. If we look into this surface, then this is a flat surface, isn't it? And I have told this thing while explaining plane mirror that the radius of curvature of a plane surface is actually infinity. So you can say that R2 is equal to infinity. Therefore, we'll put the value here. Don't worry about the sign. And if you solve this, we know 1 by infinity is 0. But let's solve this 1.5 by 1. You can write this as 115 by 10 minus 1, 1 by 20, and then if we solve this, then we will get that it is half multiplied by 1 by 20, which is nothing but 1 by 40. Therefore, we can say the focal length is 40 centimeter, which is positive. And I told you earlier that since this lens will actually behave as a convex lens, as you can see, Plano convex, the combination will ultimately give us a convex lens. Therefore, the focal length should be positive. I've told this earlier even before solving the question. So as you can see that yes, it's correct that the focal length is coming in positive and the magnitude is 40 centimeter. Therefore, this is our answer, that focal length of this lens will be plus 40 centimeter. I hope the concept is clear. Now let's move on to our second question, and this will be a bit tricky question. So let's concentrate. Okay, now let's look into this problem. It says convexo-concave lens in air, that is the lens is kept in air, and the refractive index of the lens is given to be 1.5, as you can see it here, and the focal length is given to be 24 centimeter. The radius of one surface is double the other. Find radius of curvature in centimeters, and the options are given. Okay, so you need to find out the radius of curvature for both the surfaces. You need to understand one thing, that while I was explaining the types of lenses, that is biconvex lens, plano-convex lens, concavo-convex lens, these were the classification of convex lens, and for concave lens, biconcave, plano-concave, and convexo-concave. I said that you need to remember the diagram, okay, and the property of when something is a concave lens and when something is a convex lens. One thing you need to understand, that whenever these kind of words are given, the second term always determines the final result, that is whether the lens is a concave lens or convex lens. For example, we have gone through this, that biconvex. What does this mean? This means that the end result will be a convex lens. Plano-convex, if I write plano-convex, what does the second term means? The second term means that the combination of both the surfaces will ultimately give us a convex lens. Similarly, we can say that concavo-convex lens. In this lenses, there are two surfaces, one is concave, one is convex. The combination of the two surfaces will ultimately give us a convex lens. The second term tells us what is the end result of the lens, whether it's a convex lens or a concave lens. Okay, so simple as that. As you can see it here, that it's a convexo-concave lens. Therefore, we can say that the end result will be a concave lens. Okay, and we know the focal length of a concave lens is negative. Okay, so you need to remember this. Another thing I told you, that for a convex lens, what I've told you, that for a convex lens, the edges are thin and the center is thick, and for concave lens, I said that the edges are thick and the center is thin. If you haven't gone through that video, please go through that video. The name of that lecture is Introduction to Lens. So please go through that introduction of lens and you'll get the figure, because if you don't know how this convex or concave lens looks like, you can never solve this problem. Okay, so let's see. Let's draw the diagram. So convex or concave looks like this. The edges should be thick, as you can see, and this is our first surface. Okay, and this is our second surface, a little bit curved. Okay, as you can see, this is our R1 and this is our R2. The edges are thick, okay, and the center is thin. I've explained this, so if you haven't gone through that video, then please go through that video and things will be very, very clear. Once you can draw this figure, then things are simple. Now just put the value and you'll get the answer. Now you know Lensmakers formula, that 1 by f is equal to refractive index of the lens divided by refractive index of the medium in which the lens is kept minus 1 multiplied by 1 by r1 minus 1 by r2. So the focal length is given to 24 centimeter, and we know the ultimate result will be a concave lens. Therefore, the focal length will be negative. We know the focal length for a concave lens is negative. So you can put that 1 by f to be 1 by minus 24. Simple as that. And refractive index of the lens is given to be 1.5. Refractive index of air is 1 minus 1. And it's given that the one surface is double the other. Therefore, you can see that R1 has to be smaller and R2 is bigger. From the figure you can see that, but both will be negative. Since the incident ray is in this direction, therefore this direction will be taken as positive, and we'll be measuring radius in this direction because this is the pole for both the surfaces. Therefore both the radius will be negative. So if we take R1 as R minus R, then R2 can be written as minus 2R. Now if you go on solving this, then we will get that 1 by minus 24 is equal to, this can be 1.5 by 1 minus 1 can be directly written as half, and this can be written as 1 by 2 r, minus minus will become plus, and this will be 1 by r. You can solve this, okay? You can pause the video and solve this and you'll get the result. Okay, so this will be this got cancelled, 12, so minus 1 by 12 can be written as like this is equal to 2r is the LCM, and then we can turn 1 minus 2, or 2 and 12 will get cancelled, 6, and we will get minus 1 by 6 is equal to minus 1 by r. Minus minus got cancelled, therefore you can say that r is actually 6 centimeter. Okay, if r is 6 centimeter, then we have taken r1 as r, if you look here, and r2 we have taken as 2r, therefore the radius r1 will be 6 centimeter and r2 it will be double of that, that is 12 centimeter. Now if you check the option, then option B is the correct answer. I hope the concept is clear. If you just understand, if you just have the concept and if you know how the figure looks like, how the lens looks like, then you can easily solve this problem. Okay, once you can figure out the diagram, then it's just basically the formula, just put it and you'll get it. I hope this is clear. So this is why concept is very important. You need to build your concept and things will automatically flow. So this is all for this problem. Now let's move on to our next problem. Now let's look into this concept. Before moving on into our next numerical, you need to understand this concept and then we will solve numerical based on this concept. Okay, so let's look into this concept. It says that if the refractive index of the lens is smaller than the surrounding, see, for Lensmakers formula, we know that this is mu L divided by mu M minus 1 multiplied by 1 by r1 minus 1 by r2. Isn't it? This is the formula. So from the formula we can see that the refractive index of the medium in which the lens is kept is very important. So it depends, the focal length depends on that. So we can say that it is seen that whenever a lens, suppose this is the lens and this is refractive index of the medium, this is refractive index of the lens, if the refractive index of the medium in which the lens is kept is bigger, okay, bigger than the refractive index of the lens, then what happens is convex lens starts behaving as a concave lens, or you can say starts behaving as a diverging lens, because concave lens is also known as diverging lens. Or we can also say that concave lens starts behaving as a convex lens or converging lens. Okay, so as a whole we can say that what happens actually, the behavior of lens changes. Okay, this is very important. Whenever a lens is kept in a medium such that the refractive index of the medium is greater than the lens, then the behavior of the lens changes. That is, convex starts behaving as a concave and concave starts behaving as a convex. Now, how can you prove this? From the Lensmakers formula, look into this formula and things will be clear. Now let us consider that this is a biconvex lens, okay, such that R1 and this is R2, which are equal. Okay, so R1 equal to R2. Now let's understand, analyze this formula. We can say that 1 by f. We know that for convex lens, the focal length is always positive, isn't it? So let's analyze mu L mu M minus 1. Now 1 by R1, if you look into this figure, then R1 will be positive. So R1 will be positive minus R2 will be negative, isn't it? Therefore, we can say that 1 by minus R2, which ultimately can be written as minus minus will become plus. So you can write it in this way. Now if you look into this formula, you'll see that this term is always positive because both terms are positive. The only remaining thing is this part. Now if mu L is smaller than mu M, then what will happen to mu L divided by mu M? It will be obviously less than 1. Okay, if mu L is smaller than mu M, then this division will be less than 1, and if this division is less than 1, therefore we can say this term will be negative because this term is smaller than 1. So we are subtracting 1, therefore this thing will be negative, and we can see the focal length becomes negative. But we are dealing with convex lens, as you can see it here, and we know convex lens, the focal length is positive. But since mu M is greater than mu L, we are getting negative for focal length, okay, which ultimately tells us that the behavior of the lens changes when the refractive index of the lens is smaller than that of the surrounding. I hope the concept is clear. Now we will be looking into one of the problem based on this concept so that things becomes more clear. Now let's jump into that numerical problem. Okay, now let's look into this question based on the concept that we have recently gone through. So let's solve this. Okay, it says a convex lens of refractive index 3/2 has focal length 20 cm in air. Okay, the lens is immersed in a fluid of refractive index 2. Find new focal length and nature of lens in this fluid. How to solve this question? Let's see. Okay, now if you look into this question, you'll see that there is no mention of R1 and R2 here. So how to solve this question? Okay, let's build the equation first, that is using the Lensmakers formula. So that is 1 by F is equal to mu L by mu M minus 1 multiplied by 1 by R1 minus 1 by R2. Okay, so the first equation says that the focal length when the lens was kept in air was 20 centimeter. Now this is a convex lens, therefore the focal length will be positive when kept in air. So 1 by 20 is equal to refractive index of the lens is given to be 3/2 and that of air is 1 minus 1, and we don't know the value of R1 and R2. So leave it in this way and we got this is our first equation. Now if we look into our second statement, the lens is immersed in a fluid of refractive index 2. So again we can use this formula that we need to find the focal length here. Okay, now the refractive index of lens, we know it's 3/2, and refractive index of the medium, that is the fluid in which the lens is kept, is given to be 2. So we can write here 2 minus 1 multiplied by 1 by R1 minus 1 by R2. Okay, now how to solve this? This is purely mathematics. You need to use the concept of maths, that whenever these kind of things comes up, what you need to do is, if you look into this equation carefully, then you'll see that this term and this term is similar and it is multiplied with the first term. So the easiest way to get rid of this term is to divide the equation. Okay, so these are the techniques that you need to remember. Okay, this is basically mathematics. Okay, so we will divide equation 1 with equation 2. So dividing equation 1 with equation 2, we will get that 1 by 20 divided by 1 by F is equal to 3/2 minus 1 divided by 3/4 minus 1, and this term will get cancelled out. Now we have one equation and one unknown, that is F. Okay, now if you solve it here, okay, so we will get that F by 20 is equal to, now 3/2 minus 1 can be written as 1/2 divided by 3/4 minus 1 can be written as minus 1/4. Now things are simple. Now F can be written as 20 multiplied by 2. Okay, and the minus sign will come up here. So we can see therefore focal length is equal to minus 40 centimeter. As you can see, this is a convex lens and we know that convex lens has a positive focal length. But if you look into the answer, then you can see that the focal length is actually negative, which suggests that the focal length of convex lens is not always positive. You need to understand that the focal length of convex lens is positive only when the lens is kept in a medium that has a refractive index less than the lens itself. If the medium in which the lens is kept is having a refractive index more than the lens, then the focal length of the convex lens will be negative. That means the convex lens will actually act as a concave lens, or we can say the rays after refraction will diverge instead of converging. Okay, I hope the concept is clear. Now let's move on to our next question. Now let's look into this problem. Now I haven't given any question based on lenses formula, so we'll be using that formula in order to solve this question. One thing you need to understand, that whenever no refractive index is mentioned and you need to find out focal length or image distance, then in that case you need to use lenses formula. But whenever focal length is given and refractive index is mentioned in the question, then you need to use Lensmakers formula. This is very important. Okay, so now let's see, since no refractive index is mentioned here, therefore we won't be using Lensmakers formula, we'll be directly using lenses formula here. The lenses formula is very simple. 1 by F is equal to 1 by V minus 1 by U, isn't it? Now it says find the position and nature of image. That means you need to find out the value of V here. Okay, and from the figure you can say that this is a concave mirror, therefore the focal length will be negative. It says it's 10 centimeter, therefore we can write F should be minus 10 centimeter and U will be minus 5 centimeter according to sign convention. Okay, now directly we can say that V is equal to uf divided by u plus f. Okay, so u is minus 5, f is minus 10 divided by u is again minus 5, and this is minus 10. Okay, now if you solve this, then we'll be getting 50 divided by minus 15, which is 5 3 are 15, and 10 by 3, so we are getting minus 10 by 3, which can be further solved and written as 3.33 centimeter. Therefore, we can see that the image that is produced is at minus 3.33 centimeter. That is 3.33 centimeter. Negative sign indicates that it is moving in the opposite direction to that of the incident ray from the pole, because the measurement is done from the pole. Therefore, we can say if this is the pole, this is the direction of incident ray, so it need to move in this way, and this will be the position of the image, that is 3.33 centimeter. Simple as that. Now this is the position. What will be the nature? The nature of the image is virtual. Okay, so we can say the nature is virtual. Why virtual? One thing you need to understand, when the image and the object are on the same side of the lens, then we say that the image that is produced is virtual. This is one way of looking at it. Another way of looking at it is that if u and v has same sign, okay, as you can see it here, the u has minus sign here, that is negative sign, and v also has a negative sign. Since u and v have the same sign, therefore we can say the image produced is actually virtual. Now another way is that you can find the ray diagram. Okay, now we know the image will be produced here, but how it is happening? The ray diagram is like this. We require two rays. So this is our first ray, and this is our second ray along the principal axis. So this will go undeviated along the principal axis, and this after refraction will diverge because it is a diverging lens, concave lens. Since this ray and this ray are diverging in nature, they will not meet in the forward direction. So what we need to do, we need to extend it backward, and we see that the intersection point is taking place here. Okay, and the intersection is a false intersection, not real intersection. Therefore we can say that the image is actually virtual. I hope the concept is clear. So your concept should be as solid as possible, like crystal clear. Okay, whatever may be the question, bam, you can solve it. Okay, so that's why I always stress on concept rather than tricks. Okay, tricks may help sometimes, but if your concept is good, no matter what the question is, you can just bang the question. Okay, now let's move on to our next question. Okay, now let's look into this problem. This is the final problem of the video. So let's see. A concave or convex lens or refractive index 1.5, this is given, is kept in a fluid or refractive index 2. If the object is kept 40 cm in front of the lens, find the focal length. So the first thing that we need to find out is focal length, and the figure is given here that this is a concave or convex lens, and we know since this is ultimately a convex lens, therefore the edges will be thin. As you can see, edges are thin and the center part is thick. This thing has been explained in the introduction of lens video. Okay, and it says the radius of curvature of the first surface is 40 cm and the second surface is 20 cm. So we'll be using Lensmakers formula in order to find out the focal length. So 1 by f is equal to mu L by mu M minus 1 multiplied by 1 by R1 minus 1 by R2. Okay, so refractive index of the lens is given to be 1.5. Refractive index of the medium is given to be 2 minus 1 by R1. Now R1 should be used with correct sign. Okay, so here it is given 40 cm, but you can see that since the rays are coming in this direction, therefore we need to calculate R in the opposite direction from the pole. Therefore R1 will be negative, so it will be minus 40 minus of R2. R2 is again negative, as you can see it from the figure, so it will be minus 20. Now if you go on solving this, you'll get 1 by f is equal to minus 1 by 160. Okay, therefore you can say the focal length is minus 160 centimeter. As you can see that though it is a convex lens, focal length should have been positive, but since the lens is kept in a medium having refractive index more than the lens, therefore the nature of lens changes, and now the convex lens is acting as a concave lens. Therefore this lens will actually, instead of converging the rays, will diverge the rays. Okay, therefore we can say the nature, the second question, nature of the lens will be diverging. So don't write converging looking into the convex lens. Okay, now for the third part, that is in order to find the image location and nature, let's see. In order to find image location and nature, we'll be using Lens's formula, as we know that 1 by f is equal to 1 by v minus 1 by u, isn't it? Now we need to find v. Therefore, we can directly write that V is equal to UF divided by U plus F. Now, the value of U and F should be used with proper sign. So, we'll be using that. We know U is equal to given to be 40 centimeter in front of the lens. Therefore, it will be minus 40. And F, we have already got that it is minus 160. And U is again minus 40. Plus of minus 160 is again minus of 160. Now if we solve this, then we will get minus 40 multiplied by minus 160 divided by minus of 200. So 0, 0, 0, 0 got cancelled. 2 2s are 4, and we will get minus 32 centimeter. Okay, so we got minus 32 centimeter as the image location. That means if we analyze, our U is actually minus 40 centimeter and our V is minus 32 centimeter. So since both the sign are same, we can say that the image is produced on the same side as that of the object. Therefore, since the image and the object are produced on the same side of the lens, therefore the image is actually virtual in nature. Okay, simple as that. Therefore, we got the image location to be minus 32 centimeter and the nature is virtual. I hope the concept is clear. So this is all about this video. I hope all the concepts that I've talked about and all the problems that I've showed is super simple now. And if questions are asked based on these concepts, then you can smash those. Yeah, so this is all for this video. If you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.